Alright, welcome to FRQ number 1 for set number 7. So we're given this diagram right here. There's a cart being pulled, and there is a string and a force sensor and a motion sensor. And then it says friction is not negligible. And part A wants us to draw a free body diagram. So let's go ahead and draw our box or our cart. Okay. Alright, so those are all the forces acting on our cart. We have our F of N, F of G, pretty standard. And then we have T, because there's a string here that's pulling it. And then it said friction is not negligible, so that means friction is there. So we have our F of K. Oops. Alright, part B would like us to plot the points, clearly scale, draw a straight line. Okay, so we're plotting. Okay, so now it gives us this data because the student repeated several trials. So it gives us this data table, and now it wants us to plot this data onto this graph. Okay. Okay. This one. Alright, now we just plot all the points. About there. Okay. Right. And it wants us to draw a line. So when I do best fit lines, I normally connect the first point and the last point. Okay, so that is our graph. Okay, so part B's. Right, and then part BI says using the straight line on the graph, calculate the mass of the car. Okay, so looking at our graph, we can see that it gives us force and acceleration. And to me, that signals Newton's law. And so we're given force and we're given acceleration. We want to find mass. So to find mass, that would be force over A equals M. Okay, so so since I connected the first and the last points, I can use those coordinates as my numbers for my straight line. Okay, so acceleration is our rise, and our run is force. So normally if you use normally you would use the slope of a line to find things, but looking at it here, as you can see, we have to do force divided by A, but our slope is A over F. So instead, we're still gonna find like the rise and the run, but we're just gonna flip it in order to fit this equation that we found right here. So A, so you have 0.7 minus 0.12, and then you have 0.6 minus 0.32. Okay. Okay, and remember that was A and that is F, so we need to put 0.28 over 0.58 to satisfy this. It's going to be equal to M, and then you get mass is equal to 0.48 kilograms. Okay. I determine the magnitude of the force of friction. Okay. So force of friction, it tells me we need to set up newtons again. Okay. So, looking at a free body diagram, we know that the cart isn't moving up or down, it's just moving to the right, so we're going to be looking at our forces in the x direction, so our t and our k, and it's moving, so that tells us that t is bigger, and f of k is smaller, big minus small, and then, ma. And then you can just pick one of your data trials. One of the trials from the data chart, just pick one, and that's what you're going to plug in. So I'm going to use number 5. So it tells us that t is 0.6 minus f of k, and we just found mass, 0.48, and the acceleration for that was 0.7. Okay, so now I just go ahead, simplify. Right, so we want to get f of k by itself, so that means we'd move f of k over here, add it, and then subtract this onto this side. That is the f of k. Okay, part C. So what does it tell us now? The above experiment is repeated using a constant force sensor reading 0.45. The car starts some rest at timer t equals 0 and is pulled for a time 2 seconds along the dynamics tracks. Determine the acceleration of the cart. Okay, so tells us force, so pretty simple. We're just going to set up newtons once again, and again, t minus f of k equals ma. it tells us that the new T is 0.45. Okay. And we just found f of k. So I'm just gonna go ahead. So we're writing this f of k we just found here. And we found a mass. And now we're looking for A. Now let's go ahead and simplify. And solve for A. Okay. On to part D. Okay. I'm sorry if my voice sounds softer, it's because I have really bad bug bites right now, so I keep moving around. Okay, the string breaks at t equals 2. Calculate the time it takes for the cart to stop after the string breaks. Okay, so what I'm going to do first is find its new acceleration once the string breaks. So when the string breaks, looking at our diagram again, when the string breaks, the only force is f of k. So that will still cause an acceleration. So I want to find that acceleration. So f of k equal to ma. Okay. So this is going to be 0.264 equal to mass 48A. Okay, now I'm gonna put a negative here because f of k acts against you. And we know that the cart is moving to the right. F of k is pointing to the left, meaning it's going to be working against you, which also means it's going to decelerate the cart, meaning that it's going to have a negative acceleration. So that's why I'm putting a negative there. I'm going to just go ahead and solve for A. Okay, so we have found the new acceleration. Okay, now what I want to do is find, so now what I want to do is find VI. So remember, it's being pulled by this force right here for 2 seconds. So that means it's going to get to some sort of speed. I want to find that speed because that will help me find time. So I'm going to use my VF formula. Okay, so now instead of using this acceleration, I'm going to be using this acceleration because this is the acceleration with that 0.45 tension during those 2 seconds. So remember, I'm trying to find the velocity at the end of those two seconds. So that's why I'm using this acceleration. And then 2 seconds plus 0 is at rest. Yeah, starts from rest. Okay. Okay. So that is our VF, or V at 2 seconds. Okay. So using this same formula, we're going to find time. So it wants to know how long until the car comes to a stop. So that means VF is 0. Now we're using this acceleration because that is the new acceleration for this scenario. So this is the acceleration after 2 seconds. And that's what we're finding. We're finding time after the 2 seconds. Plus our VI, which would be our V at 2 seconds. Okay. So we want to isolate for T. Okay. And you get 1.41 seconds. Alright. Part E. So now it tells us the experiment and analysis in parts A and B are repeated with a cart that has the same mass but a greater force of friction. Will the slope of your new line be greater than, less than, or equal to the slope of your line in part BI? Okay. So it is going to be less than. Alright. So if your f of k increases, so this increases, correct? Looking at it, what can I use? Okay, I can just use this one. Okay, yeah. So looking at it, if your f of k increases, that means more is being taken away from t, which means your acceleration is going to decrease. Now, when your accelerations decrease, that means your slope is also going to decrease. It's not going to be as steep. It's going to, so your slope is like this, but with an increase in f of k, your slope is slowly going to go down like this because your accelerations are going to decrease, because now more is being taken away from the tension. Yeah. So let me explain it one more time. So if your f of k, here, let me write this out. Okay, so you have your t minus f of k equals ma. If this increases, that means your t, more is going to be taken away from it, which means less is going to be going into acceleration, meaning your accelerations are going to decrease. And looking at our chart, or our graph, it's an acceleration versus force. So assuming that your forces don't change, but there's more friction, your accelerations are going to decrease. Because like I said, if f of k increases, you subtract f of k, which means more is going to be taken away from t, making a decrease. So your slope is going to decrease because your accelerations are going to decrease. Yeah. So that concludes FRQ number 1.